Geometry Unit 8, Section 4, Right Triangle Geometric Mean Theorems. So what we have here is when the altitude of a right triangle is drawn from a right angle um, to the hypotenuse, we get an image like this. So the original triangle we were working with here was this triangle ABC. And B was the right angle, AC is the hypotenuse. So an altitude goes from a from an angle to the opposite side. It has to be perpendicular to the opposite side. So that's what this is this is an altitude drawn from right angle B to the hypotenuse, and it's perpendicular to that hypotenuse. And what happens here when that happens, whenever we have a right triangle with the altitude from the right angle to the hypotenuse, we get two other right triangles. Because if this is perpendicular in here, then obviously this is a right angle and this is a right angle. And so these two sub-triangles here are also going to be right triangles. But it's not just more right triangles. We ended up with two similar sub-triangles to each other, but also to the original. So we end up with three total triangles. I call them the large, medium, and small triangles. The large one's the original, triangle ABC. The medium one here would be on the left side, and then the small one is over here on the right side. And all three of these triangles are similar, and so what that means is we know all the angles, corresponding angles are congruent, but the sides are proportionate. And creating proportions with the sides here, we get some interesting things since a lot of them share the same sides or same pieces of sides. And so we get what we call geometric mean formulas. But let me explain that further down here. First, let's just list the corresponding angles in order for these three triangles. So the large triangle, we could pick any order, but let's go with ABC. So triangle ABC. And so B, our middle angle is going to be our right angle. A would be the, of these two, A would be the smaller of these two acute angles. They look pretty similar, but I could decide BC is definitely smaller than AB. So that means the angle opposite it is smaller. So this is the smaller I'll do with a single slash, and the larger of the two acute angles I'll do a double slash. So I'm going smallest acute angle, right angle, larger acute angle. All right, so the medium triangle in here, what would that correspond to? Now, first of all, the right angle for this triangle, the three letters are A, B, and D, but I got to get them in the right corresponding order. D is definitely the right angle, so that's going to be in the middle. But which of these two angles is the smaller acute one? Well, the smallest side of this triangle is BD, and that's opposite angle A, so that's going to be the smallest acute angle. And then we would have the next smallest angle in here, so that would be B. So ABC of the big triangle corresponds to ADB of the medium triangle. So this angle in here is the same measurement of this angle here. And I really wouldn't call this angle B, I'd have to call it like ABD. But these two angles will have the same measurements. And then a small triangle, this small triangle in here, again, D is going to be my right angle. And DC is the smallest side, so that means that this angle up here is the smallest angle, B, and C is the larger of the two acute angles. So ABC corresponds to ADB for the medium, and BDC for the smallest. It might be helpful to put angle measurements in here, like let's say this is, it's not, but let's say, 30, 60, 90 for simplicity. This would be a 30-degree angle. This would be a 60-degree angle. Well, this one would also be 30 degrees because the three angles here add to 180, right? And so I see that angle does match this angle, so that's why angle B for the smallest matches angle A for the largest, right? Angle B for the largest, angle B for the smallest. And angle A for my medium triangle is angle A for the large triangle. That's why they overlap, so that's why it's going to match there. And for this triangle in here, this would have to be 60 degrees because the three angles add to 180. And so so we can see the corresponding connection between these, that a lot of them are upside down and rotated and stuff like that. We could describe a sequence of similar transformations, of course, to get them on top of each other, but it would be a lot. But we get three similar triangles here. All right, so if we talk about some of the side proportions, to help us, I drew another figure here, and here's the altitude of the big right triangle to the hypotenuse over here. I labeled the sides with lowercase letters. So I could talk about this side as A, this one is D, this one is B, and then this whole hypotenuse of the big triangle is C, but it's divided into two sections, one of E and one of F, because they're parts of the other triangles there. And there's three proportions we want to take a look at, and they're going to create what we call geometric means. And the definition of a geometric mean is the geometric mean of two numbers is the square root of their product, for their product. I think that's a very confusing phrase, so let me show you an example of what I mean. So if I do this, small triangle, long leg. So here's my small triangle. This is my hypotenuse, short leg, long leg. That would be D. And then small triangle, short leg would be E. And that's going to be proportionate to the medium triangle, long leg, short leg. And that would be F to D. F to D, yes, F over D. But what we notice is that D is a common side for them. But it's not the same side. Like D is the long side of the small triangle, and it's the short side of the medium triangle. But when we cross multiply this, we get D squared equals E times F. And so what we would say here is that D is the geometric mean of E and F, because to solve for D, you'd have to do the square root of E times F. And this is very confusing, I think, without numbers, but basically one way to think about this is that the altitude, the one number or side length that's in the whole figure, because all the other ones are on the outside, the one that's in the inside, that squared is the two parts of the hypotenuse times each other. So this squared is going to be that times that. And so we say D is the geometric mean of E and F. But I wouldn't even worry too much about the vocab behind it. Just know that if I gave you this is X and this is 2 and this is 8, you could do X squared equals 2 times 8 and solve for X. And so that's really what we're talking about here, is we don't need to create proportions if we remember these shortcuts. And this, which might actually, I don't know if it's on the bottom of your first page or on the top of your second page, might have got cut off. That was for this, that D is the geometric mean for the parts of the large hypotenuse, E and F. Two other ones like this. Small triangle's hypotenuse is A. Small triangle's short leg is E. Large triangle hypotenuse is C. And large triangle's short leg is A. And so this multiplies to be A squared is E times C. And so what we're saying is that the leg of this big right triangle, that squared, is the part of the hypotenuse attached to it and the whole thing C. So this squared is E times C, the part attached to it and the whole thing squared. And so that's what this is kind of saying here. And then one more proportion like that. Medium triangle's hypotenuse is B. Medium triangle's long leg F. Large triangle hypotenuse C. And large triangle long leg B. We get B squared equals C times F. And so that's this leg of the big right triangle is the part of the hypotenuse attached to it and the whole thing. These two are related to each other. Sometimes we refer to them as leg theorems because these are the two legs of the big triangle, and they're each the part of the hypotenuse attached to them and the whole thing. The part of the hypotenuse attached to them and the whole thing. So these are basically the same formula but on two different sides. It's this one over here that's kind of on its own, that this piece in the middle is the two parts times each other. So it's using these formulas. I think they're a little weird when you first hear them, but then when you practice them, and I'll show you, do some examples for you quickly now, but then when we practice them in class, you'll see that just remember what goes where, and they're actually pretty easy problems. So AD5, DB20, find CD. So because this is the piece in the middle, this squared is the two parts times each other. So you get x squared is 5 times 20. X squared equals 100, x equals 10, CD equals 10. That's it. So you don't need to create a proportion. You can just remember that the altitude squared is the parts of the hypotenuse times each other. AD is 3, AB is 12, find AC, put that X. So this is one of the legs squared. And really it's these three things are the things that these pieces squared have to do with the large triangle hypotenuse, either the two pieces or a piece in the whole thing or this piece in the whole thing. So 3 times 12, so we would end up with x squared equals 3 times 12, x squared equals 36, x equals 6. So AC equals 6. If we had the other side, like say we wanted to find this side, we would need this piece times the whole thing. And so that's, the two legs. It's the part, the part attached to it and the whole thing, or the part attached to it and the whole thing. It's when it's in the middle, it's just the two pieces times each other. You don't involve the whole thing at all when it's the altitude. Here, AD is 3, CD is 6, find the length of DB. So again, the altitude, this time we have that. That squared is the parts times each other, 3 times x. 36 equals 3x, x equals 12. DB is 12. And lastly, I like this type of question. I'll probably put something like this on your test. Find all three of these things. So given this is 4, given this is 6, find these three things. So I'm going to make this x, y, and z. And find all three of those given this. So what is x squared equal? What is y squared equal? What is z squared equal? I like this because my z's look like 2s, sorry. What is z squared equal? It has all three formulas in one. So the easiest one is the middle, because that's just the two parts times each other. So 4 times 6. So 4 times 6, we get y squared equals 24. Y equals the square, I shouldn't have an equal sign there. Y equals the square root of 24, which is 2 rad 6. And we'll talk about simplifying radicals in class 2. All right, so then x and z are the leg ones. They involve the part attached and the whole thing. So I'm going to need the whole thing here, which is 10, the sum of the parts. So x squared is the piece attached to it and the whole thing. So that's 4 times 10, 40. X squared equals 40, x equals rad 40, x equals 2 rad 10. And lastly, z. Z is the leg on the right, the part attached to it, and the whole thing. That's 6 times 10. So 6 times 10, z, and sloppy z's. Sorry. 6 times 10, should have picked a different letter. Z squared is 6 times 10, 60. Z equals the square root of 60, and that simplifies to be 2 rad 15, I believe. So that's what this is, and this is the type of questions you see with it, and it's really just solving some basic algebra stuff, but you have to know how to set the questions up. What squared equals what times what, but it all stems from the fact that they're similar triangles, and we get side proportions that give us these little shortcut geometric mean formulas. All right, so we'll practice this in detail. We'll see this a bunch. Sorry, this video is a little long.